Continuing on with class 25, here's an example from Sengel. This is problem 1474, at least out of one of the editions, where we have a Francis radial flow hydroturbine is being designed with the following dimensions. We have 2 meters for the outer radius and 1 meter for the inner radius, 1.242 meters for the inner radius. B2 is 0.731 meters and B1 is 2.20, right? So those are these parameters right here, right there, and right there, right there. So that's the sizes of these. And the runner rotates at 180 RPM, and the wicket gates turn the flow so that we have alpha 2 is at 30 degrees and alpha 1 is at 10 degrees right there. So you can see that's the angle at which these things are coming in here and coming out right there. So yeah, so that's different from the betas. So we're going to have to try to find the betas. Is that right? Yeah, that's one of our goals. So the volumetric flow rate at the design conditions is 340 cubic meters per second. And the gross head provided by the dam is 90 meters, right? So that doesn't mean that's the head that actually gets consumed. That's the amount that it can be used, right? For the preliminary design, irreversible losses are neglected. Calculate the inlet and outlet runner blade angles respectively and predict the power output. And required net head is the design feasible. Well, that will be where we compare what the head we will find from this with what the head that's provided by the dam. So some of the first things that I'll do is I will find the radians per second instead of RPM here. So we multiply by 2 pi and divide by 60 to turn RPM into radians per second. So 18.85 radians per second. And we could find what the normal velocity is going to be based on the equations that we provided up here, right? So no, I'm sorry, I take that back. I had previously written these out where we could find the flow rate by taking the circumference 2 pi r and multiply it by the, let's see, what do we call those? Oh, I didn't really say what those are called. Let's call it the these heights, these right here. So what we're doing is we're really finding the area that's through there, and we can multiply that by the normal velocity right here. So let's say this is 1, 1, and 1n right there, right? So we can find 1n by taking this and dividing it by 2 pi r1 b1. So that's 340. And my dog wants to say hi. She's angry at some mailman probably. Let's see, 1.42. And so B1 is 2.2, right? 2.2. So we get for V1N as 17.32. You have to remember that's the outlet there, right? So that's that value right there because it's normal meters per second right there, right? So that's that guy right there. So V2N, which is this right in there, is going to be equal to 342 pi, and now its radius is 2, and its b is 0.731. So we get a velocity of 21.37 meters per second. Now, we're not going to use the equations from up here because we don't know what the betas are, but we do know what angle this thing is actually coming out of, coming in, and what it's actually coming out. So we can just, because these are perpendicular to each other, we can just take the tangents, right? Because what we're really doing is we found the normal, which is going to be the run of this velocity. It is a triangle, just kind of moved out, right? Parallelogram, rectangle. So we can find the run by multiplying the normal by the tangent, right? So we go alpha 1 right there. So we go 17.32 times the tangent of that angle, which see alpha 1 is 10. So that turns out to be 3.054 meters per second. And V2 and tangent alpha 2. So we have 21.37 and the tangent of 30 degrees. So we have 21.37 meters per second. And I'm going to go ahead and find my R's. My R2, I was doing 1 first, so I'm going to do 1 first here. R1 omega 1, just R1 omega, there's no 1 there. That's 1.42 times 18.85. And so he's 26.77 meters per second. And then R2 omega is 2 times 18.83. And that becomes 37.70 meters per second. And so to find the betas, 1 second. I'm gonna get a ruler. 1 second. Okay, so let's see. I guess I did the velocity 2 first. So this has some amount of, I think it's some amount of correctness. Let me switch to blue. So here is the velocity 2 coming in right there. So I'm going to transfer him with a ruler over to the side over here. Oops, try not to. See if I can move this over. There you go. Center it. So that's V2. And right there is the tangential component, and here is the normal component. Let me make it a little bit more accurate. Kind of like that. All right, so here's V2N, V2 tangential. Right there, that's the ones that we're looking at. And if you, here's your alpha 2, if you wanted to do that right there. We do know that V2 tangential is also equal to omega R 2 minus V2 normal divided by the tangent of beta 2, right there. Right, so that's going to be that's that guy right there. So what this is really saying, so we also have a tangential right there. We have try to make those parallel. Here is our R2 omega, and I don't know, is this the right magnitude? We say here's our V2 tangential. Hopefully they look kind of like the same size, like that, or sort of like that. Here's our V2 normal again. But what we want is really the relative to be like right there, right? So there's going to be like the relative velocity. That's what we would like the relative velocity to be coming in just at that position right there. So we could find to get that velocity, that relative velocity onto the thing, is to like kind of find this angle right in there. So this guy right here, he's really the V2 relative velocity that we would have right in there. So that's like that. That's like the big idea, right? So we're gonna have like actually have here's going to be the result of this right there. I think he would say no, that's not true. Yeah, okay. So anyway, I'll just go ahead and write the thing out here. I don't know why that just appeared. I guess maybe I accidentally hit it there. So we could take the beta 2 is going to be equal to the inverse tan. Am I going to have enough room? I'll make enough room. V2n divided by omega R2 minus V2 tangent. So we have all the values, 21.37. Oh, that's hard to read. I need to change what that pencil width is. Can I change the pencil width? It's 1 millimeter. Maybe I should use something else. Maybe no, that's 1 millimeter as well. Can I make him smaller? There you go. There he is. He's smaller now. Okay. Let's see if I can make him here. 21.37. That's better. Divided by omega R2, which I found as 37.70, and then subtract out V2T, which was 21. Whoops, I must have got this wrong right there. Yeah. Well, I'm not going to re-record this, so I don't think any of you are going to watch it anyway. So, oh, I must have written this wrong up here somewhere. So that's no way that was true. No. There's no way that this was correct. This was incorrect. And that must have been incorrect. Yeah, sorry about that. So this up here, oh wow, this is a terrible video. 37.01. Should have just written that all along. 37.01. And then this was correct 21.37. So yeah, they were very close to each other right there, weren't they? That's one of the reasons why I got confused. 37.01, and 21.37. And I end up with a beta of 66.19 degrees. And I double checked. I made these in SolidWorks as a sketch. But I'm not going to continue through. I was trying to make a good point here, or what I thought would be a good point in terms of trying to find these triangles and draw these triangles out. But I think I just added to the confusion of it. But making the triangles in scale actually helped me to get my mind wrapped around there. But apparently it didn't take. But anyway, let's continue on with the problem. Beta 1 is now, all we're doing is rewriting out this equation right there, and to find what the necessary beta 1 is, which is this angle right in there, that we can expect to this thing to be moving at. And it's all about, because of the normal component and the tangential component creating the actual component, but now we want to have the relative component, which is going to be like right here, be aligned with that blade, right? That's the big idea. Getting the geometry exactly correct is a nice thing to do, to be able to understand the concept, but not necessarily to plug and chug these numbers in. But we take the inverse tangent of, I'll write out the equation again. V1n divided by R1 omega minus V1 tangent. All right, so inverse tangent of V1n, which is 17.32, divided by R1, so that's 26.77, R1 times omega, and then minus the tangential one, which is small 3.054. And we end up with an angle of 36.14 degrees. So that's what we're going to recommend that we use as this blade, because this is a quote-unquote design problem. And the anticipated power that we can have here, now we're going to go back and use our Euler's turbine equation right there. So we'll just plug all those values into this. So we have the shaft work is going to be rho omega volumetric flow rate times R2V2T. And remember, that's the inlet, right? Minus R1V1T, the outlet. So the density of this, I'm going to go 999 kilograms per cubic meter for water. The angular velocity we found was 18.85. The volumetric flow rate, which was given, and then the R1, R2, which was 2 meters, and the V2T, which was 21.37, minus R1, which is 1.42, and then the V1T, which is 3.054. And what we end up with is 2.450 E8 watts. All right, so I should have given this the name here. Yeah, I'll go ahead and just rewrite this thing out there. So that ends up being 245 megawatts, right? So subtract 6 out from your E8 right there to bring it up to megawatts. And then we want to take a look at what the gross, I'll call this gross power would have been, which we could go H gross that was given up above. That was like the 90 meters. Up here, right? They told us that we had 90 meters. Go gamma, and then volumetric flow rate. So we go 90 times 9,800. Those are newtons per cubic meter. And then 340 cubic meters per second. I think it's going to be correct. Yes. And we get 300 or 299.9, 300, call it 300 megawatts, right? Therefore we're going to go, the question was, is this feasible, right? Calculate and predict the power output and required net head. We actually had the required net head. I didn't calculate that, but so it would be, therefore, yes, feasible. But all you would do is the required net head here is we would say that H, I guess I'm using it lowercase, so H required to do this would be, let's see, the W dot divided by gamma and the volumetric flow rate, right? So that would be 2.45 E8 divided by 9,800 and divided by 340. So I have my calculator. I could do that in my head. 2.45 E8 9800 divided by 340 divided. So that means we have a required 73.53 meters, and of course that is less than 90, and therefore it's feasible that we could be able to use this design. And that's the end of this example.